The last gas power cycle that we're going to take a look at in this lecture is that of the Stirling engine. And the Stirling engine is a little bit unique from the other two that we've looked at, the Otto and the diesel, in that the combustion or the heat addition takes place outside of the engine itself. And so that's why sometimes this is called an external fuel engine. The Stirling engine itself has been around for quite a few years, and theoretically it can have an efficiency to be the same as that of the Carnot cycle, given that it operates in an externally reversible manner. So, the unique aspect of the Stirling is the fact that very high thermal efficiencies can be reached theoretically, provided that we can implement some sort of mechanical device to be able to implement the cycle as designed. So what we'll begin with, just like the other cycles that we looked at, what we'll do is we'll start by looking at a PV diagram, then I'll draw out a bit of a schematic in terms of how the Stirling engine may be constructed. So let's start with the PV diagram. So this is the PV diagram for the Stirling cycle, and what is happening is we are going through a process that is isothermal, and from 1 to 2 is where we are adding the heat. So we have isothermal heat addition at the hotter temperature, the higher temperature within the cycle. And the way that that is achieved is we are adding heat while expanding at the same time. Normally when you expand a gas, it gets cool, but we're adding heat at the same time, which then maintains the temperature at a constant temperature. At the same time, when we look at process 3 to 4, that is a constant temperature process whereby the pressure is going up, and that is a process whereby we are rejecting heat, and it is a compression process. And we know when we normally compress a gas, it will get hot, but we're rejecting heat at the same time, enabling us to stay at an isothermal or in an isothermal condition. Now, another aspect of the Stirling that we have not yet seen in any of the cycles that we've been analyzing is there is what we call a regenerator. And what the regenerator does is it takes thermal energy from one part of the cycle and transfers it to another part. And so that is shown in the middle. And what is happening is heat through the process 2 to 3 is being transferred to process 4 to 1. And I'll show you in a second how that can be implemented. It's using a device that we call the regenerator. So let's take a look at a schematic of what the Stirling may look like, and then hopefully that will start to bring some clarity in terms of what this regenerator actually is. So what we have are 2 piston cylinder devices, and they're connected by a common regen or piping system which goes into the regenerator. So there we have our 2 pistons, or 2 cylinders I should say. I'll draw on the pistons now. So this here we'll label as being our hot cylinder, and this is our cold cylinder, and they are connected to one another through the center piece, which is our regenerator. Now, typically regenerators have the characteristic of high thermal mass. They're able to store thermal energy. It could be constructed out of something as simple as steel wool or a porous metal matrix that does not have high pressure drop when the gas goes through it, but it can still maintain thermal energy. So the characteristic that we would look for in the regenerator is high mass times the specific heat capacity, and we refer to MC sub P as being thermal mass. So the reason why we want high thermal mass is because when the gas goes through the regenerator, we want it to exchange or deposit, I guess you could say, transfer its thermal energy to the regenerator. And then when the gas comes back the next time, we want the thermal energy to be transferred back to the gas. Now, the working fluid that you'll be dealing with, you can have many different working fluids, but common ones that are used for Stirlings are helium and hydrogen. You can also use air, although helium and hydrogen will yield the highest thermal efficiencies or practical operation. Now, what is happening here is the gas is going from the hot cylinder to the cold and back and forth. So we have gas here and we have gas here. Some of the processes, that is 2 through 3 and 1 through 4, those are constant volume processes. And when those are taking place, the piston and the cylinder are moving in a manner, or the two pistons are moving in a manner that constant volume is preserved within our system. And so the gas is essentially going from one to the other. It's being transported back and forth. And when it goes through the regenerator, it's either depositing or leaving thermal energy. And when it's coming back the other way, it will be picking up thermal energy. So that is the example or the PV diagram, as well as the configuration of the Stirling.